Hello there, calculators. Welcome to our final video for Unit 3. This is from Section 3.11, and it is my all-time favorite calculus topic. It is that of related rates. Related rates is probably my favorite just because of the fact that it's so versatile and can be applied to so many different situations. If you read the opening paragraph here, it says, in many of the sciences, there are quantities that are related to each other but vary with time. And we are going to be looking at 4 situations today that vary with time. And almost every related rate you do will have time as a variable. It might not just look like it at first. What is extra neat about related rates is even though they might be pretty complicated, the ones that we tackle in Calc AB almost always have some way more basic mathematical skill to them, whether it's Pythagorean theorem, a little bit of trig, or some volume and area formulas. And that's going to lead us right into example number 1. Now, there are 5 examples on this viewing guide. We're only going to do 4 of them today. We'll leave number 3, actually, for you to take a peek at on your own. And what we're going to do is look at example number 1 here. So it's talking about a golfer. You don't have to draw a full scenario, but it is good if a picture is not given to draw one that makes sense. And again, this circular ripple that I have drawn here is not fancy by any stretch, but it gets the job done and it shows us what we're talking about. So when we look at these problems, we always want to draw a picture and we want to list what we know and what we want to know. So we're just going to literally write the words we know and we want, because sometimes that helps kind of cut through the confusion. What do we know? We know there's a golfer that hits a ball into the pond of still water, causing a ripple. If the radius of the circle increases at a rate of 0.5 meters per second. So because we're talking about the rate at which the radius is increasing, we want a derivative. And in this case, we would represent that derivative as dr over dt. Literally the rate at which the radius is changing over time. And that is just represented by the numerical value 0.5 meters per second. And it's asking how fast is the area of the circle increasing. So that means we want to know dA over dt, specifically when the radius of the ripple is 2 meters. So that means our radius of this situation is 2 meters. And from there, what we want to do is we want to find or think of a formula or an equation that relates these 2 variables, radius and area. I happen to know one, maybe you know it too, and that is the area of a circle is equal to pi times the radius squared. We have an equation with area and radius in it, so we are good to go. This is the best case scenario. We're going to see some others where we don't always have the best case. And then we're going to use our skills from implicit differentiation to take the derivative of each side with respect to time. That is going to force all the dt derivatives that we're looking for or have and we want to use. When we take the derivative with respect to time of a, that just becomes 1 times dA over dt. And derivative with respect to time of pi r squared, that's a power function. So 2 out in front, 2 pi is a constant, r to the first. The only addition here is because r is a different variable, we need to represent the chain rule with dr dt. And from here, we're ready to go because we have what we want, all isolated and by itself, and we have all the other information we need. So watch this, dA over dt is equal to 2 pi. Our radius in this particular situation is 2, and dr dt is 0.5. And when I multiply all that out, I get dA over dt is equal to 2 pi. The one thing we really need to be mindful of here are the units. Because this is area over time, our area is going to be in meters squared. And our time was given to us in the initial problem in seconds. And that is exactly what we have here. This is a symbolic representation of the rate at which the area is changing over time at this moment. And that's it. We could write a sentence out if we wanted to saying the radius of the circle increases, or this should say the area of the circle increases at a rate of 2 pi square meters per second when the radius of the ripple is 2 meters. But you don't need to do that. You can just, if your notation is solid, you can leave it as is. All right. I mentioned that this was the best case scenario. And as you can see, once you kind of understand how this problem works, that's not a ton of work to show. It's just about knowing what to do. And we're going to move on to example number 2, where it's not as straightforward. So, example number 2 talks about a spherical balloon. I've drawn a sphere there and just added a string to it to make it look like a balloon. And we're going to go straight into our what we know and what we want. Okay. We know a spherical balloon is being inflated at the rate, so we already know we're talking about a dt derivative of 10 cubic meters per minute. If something is being inflated, that means its volume is changing. So we got that. Find the rate, or what is the rate at which the surface area is changing or increasing. So we're going to represent that with dA dt, the rate at which area is changing over time. And then it gives us a specific radius of the sphere at 3. Now, in a perfect world, we want a formula or an equation that relates volume and area. I don't know of a single equation that does that. I do know of 2 equations that have to do with a sphere's volume and area, though. The volume of a sphere, in case you don't remember, is 4/3 pi r to the third, and the surface area is 4 pi r squared. Neither of those have both variables in them, but with those powers combined, we might be able to do some damage. So what we are going to do is we're going to pick one, and the way we are going to pick the first one is by taking the variable that we know a little bit about. And so I'm going to set up at the top of my page here, v equals, I'm going to just write the formula that I know, and then I'm going to take the derivative with respect to time, and I'm going to kind of proceed like I did in the problem before. So the derivative with respect to time of capital V is just dv dt. Another power rule here, I end up with 4 pi r squared dr dt. Okay, it doesn't have dA dt in it. It doesn't have the derivative we want, but that doesn't mean we've done the wrong thing. It means we need to keep going. So here we go. I do know what dV dt is. That's 10 cubic meters per minute. 4 pi is a constant. We're using r of when the radius is 3, and then we have this unknown of dr dt. Well, we have the information to at least solve for that unknown, and maybe that will be helpful. So I get 10 equals, this becomes 36 pi times dr dt, which means dr dt is equal to 10 over 36 pi, which we can reduce that to 5 over 18 pi meters per minute. All right. That might not look like it's done anything for us, but watch what we can do. Now that we've kind of tackled the first formula, now we're going to look at the volume formula, or the area formula. A equals 4 pi r squared. We're going to take the derivative with respect to time, and we're going to get dA over dt equals 8 pi r dr dt. if we had started here with this formula, we would have ended up with 2 unknown values. But because we started with volume, we know what dr dt is. It's that 5 over 18 pi. So now I am just going to plug in the values that I know. dA dt, still unknown. 8 pi. Radius is 3. dr dt is 5 over 18 pi. We have some variables that cancel out, the pi being that main one, and we're left with a value of 120 over 18. I can reduce that. I could get 40 over 6, and then 20 over 3, which is approximately equal to 6.667. Because it's area, we're talking meters squared per minute. And that is exactly what I was looking for, because go back to the problem and make sure you are answering the question they gave you. They were asking, find the rate at which the surface area of the balloon is increasing. And we have the change in area over time is happening at a rate of 6.667 meters squared per minute. Cool. We are going to skip number 3. That is going to be something that you can work on your own. We'll eventually post a key here on the YouTube video, and you can ask your teacher about this, or me. If I'm not your teacher, I'd be happy to talk you through it. For the sake of time, we're going to bounce down to number 4. Number 4, again, I've drawn a picture for you. More often than not, you will be given a picture unless it's a very simple scenario. And here we have a person standing at the end of a pier or a dock or a boardwalk, whatever word you have for that, kind of this platform out over the water, pulling a boat by a rope at the rate of 2 meters per second. The end of the rope is 3 meters above the water level. How fast is the boat approaching the base of the pier when 5 meters of rope are left to pull in? We have a lot going on here, but the picture helps us out a lot. Here is what we know. And we're going to label the diagram too, and that's going to help us out. Here is what we know. The rate at which the rope is being pulled in, something dt, is equal to 2 meters per second. And in this diagram, I've labeled the rope as r, so the rope's length is changing at 2 meters per second. And to be precise here, it's actually changing at negative 2 meters per second because the amount of rope left out is decreasing. Check. The end of the rope is 3 meters above water level. So that is this distance. How fast is the boat approaching the base of the pier? So we are wondering how fast is the base of the boat, which is represented by y. So we want to know what dy dt is. We want dy dt. When how fast is the boat approaching the base of the pier when 5 meters of the rope are left to pull in? So we also know that r is equal to 5. Now, we are looking for any sort of equation that that includes the length of the rope and our y value. And the key here is that this is a right triangle. So for us, it is going to be the Pythagorean theorem, and it would look like this. 3 squared. The height of the rope off the water is never changing. You are not moving. You are staying, if you are the person pulling in the boat, you are staying with that rope 3 meters above the dock. Even if the rope gets shorter, you're still pulling it in from that same height. So we can keep that number constant. Plus y squared. We can't use a value here because the boat is coming in. That value is changing, equals r squared. And that's obviously changing because of the rope. So what we're going to do is we are going to take the derivative. So in other words, we're going to actually simplify this first. 9 plus y squared equals r squared. We are going to take the derivative of both sides with respect to time. And the derivative of 9 is 0. So on the left side, I'm just left with 2y dy dt. That is equal to 2r dr dt. All right, we have 4 values here. We're only supposed to have one unknown. 2y. Do we know what y is? Well, we know that r is 5 meters. We know that the person's hand is 3 meters above the ground. So I would argue that we know, because it's a Pythagorean triple, that y is 4 meters. So watch what we can do. 2 times 4. dy dt is what we want. So that is going to stay unknown. 2 times r. We were told that the length of the rope is 5 meters at this point in time, and that it was being pulled in at a rate of -2 meters per second. And once we simplify this, we have a pretty basic algebra problem. We have 8 times dy dt is equal to -20. And then when we divide by 8, dy dt is equal to -20 over 8, which is the same as -5 over 2, which is the same as -2.5 meters per second. And that means the distance of the boat and the rate of the distance of the boat from the dock is decreasing at a rate of 2.5 meters per second. All right, at any point in time, make sure you're pausing here, make sure you're going back, make sure you're digesting. The picture helps a lot here, as does picking the right formula, and that is something you will get better at as time goes on. Okay. Number 5 is a pretty cool one. It's a pretty tricky one, but it's one we can do together. A revolving light located 5 kilometers from a straight shoreline. So that's what we have here. Think of it almost like a lighthouse out in the water, though. Is turning at a constant angular speed of 3 radians per minute. With what speed is the spot of light moving along the shore when the beam makes an angle of 60 degrees with the shoreline? Holy moly. Here we go. Here's what we know. Even if you get stuck with a problem like this, always write down what you know. We know that the angular speed, in other words, the rate at which an angle is changing, is equal to 3 radians per minute. We know that we want to know the rate at which that beam of light is coming across the shore. So that actually gives us, or tells us, that we are looking for dx dt. And it would be important to put the angle where it belongs, which is here. That angle is the one that's changing, and this angle is the one that's 60 degrees. So looking at this picture, looking at what we know and what we want, is there an equation we could set up that relates theta and x without any other unknowns? And I would argue that yes, there is, because if we took the tangent of theta, that's the opposite over the hypotenuse, well, that would be x over 5. And if we are looking for dx dt, let's just go ahead and get x by itself by multiplying both sides by 5. And here we have an equation relating x and theta. Now, it's actually really not much more difficult than this with a couple tricks. Here we go. D over dt of both sides. So we are left with dx dt, which is good. That's what we want to find. The derivative of 5 tangent of theta would be 5 secant squared of theta times d theta dt. All right, we should be able to fill everything in already. dx equals dt. So 5 secant squared. What is theta? A lot of people might put in the 60 degrees, and then they would have to be like, oh, wait, we are actually talking about 30 degrees. But then you would have to be, oh, wait, our angular speed was given to us in radians. So we need to represent that 30 degrees in radians, which hopefully you remember is pi over 6. And then we were told the radian, or the angular speed, was 3 radians per minute. When I multiply this all out, that is 5 over the cosine of pi over 6 squared times 3. Well, the cosine of pi over 6 is the square root of 3 over 2 squared times 3, which is 15 over 3 fourths, which is actually equal to 20 kilometers was our distance per minute. I've been doing these problems for a long time, and when I was a student in AP Calculus many moons ago, I struggled with related rates a lot. It takes time and it takes practice doing these different problems. Please make sure you're talking with your teacher as soon and as fast as you're able to work through these problems. Make sure you're looking at the problem set as soon as you finish this video, and make sure you are using every resource at your disposal to help you with this. It has been a pleasure working with you again. Please let me know if you need anything else. I'll talk to you soon.